we have parent node, right? And we have child node. Okay, one parent node can have multiple or zero child node. Okay, one child node only have one and a single one parent node. Okay, and for those child nodes belongs to who's had the same parent node, like B and C here, right? They are also called siblings, right, with each other. And I give you the whole tree, right? Any below node is a subtree of the whole tree. Okay. Also, we're talking about a leaf node, right? Whenever a node without any child nodes, okay, they're called leaf node. Okay, and the line connects between two nodes we call edge. Okay, so that is all the term you need to remember for the tree data structure, right? And we will also talk about level. The root node is level 0. We'll go down level 1, level 2, level 3, and you're gonna see there could be multiple nodes, even they are not siblings, but they're on the same level. We call them level nodes, right? The nodes on the same level. Okay. And then we're talking about the different type of the tree, right? Mainly depends on how many child nodes one node can have. Okay. And to simplify our section here is we mainly talking about the binary tree. Binary tree, right, has all the properties of the tree, and at most, which means 0, 1, 2, right, child nodes for a single parent node. Okay, and if I have two child nodes, right, you have a left child and right child, right? In our node class, we're using left and right reference, right, pointing to different nodes. Okay, and we also have example to compare, right, or to judge what are the binary tree. If they are the binary tree, I mean, the judge is based on what? Based on if one node has at most two child nodes, okay? And even in the very edge case, is one child is always have only one child node, right? One parent node always have one child node, and it looks like a chain or one dimension of the chain of nodes. Okay, so that's where edge case. Okay, we're talking about why do we need tree structure, right? Inside use cases, right? Today we may also learn about more about how we insert a node into the tree and how we search a node from the tree. Okay, so from that use cases, right? You can figure out, hey, it has advantage, right? It has advantage by using tree data structure in some scenarios. Okay, and also because the tree consists of nodes, right? Nodes have a pointer, can point to another node and point to another node, right? So we said there's no upper limited for the nodes or tree. Okay, the tree can expand as big as possible. Okay, and we learn how to create a binary tree, right? Basically, we only have one node class, and then we define nodes, right? We define nodes. You can connect each node by setting the left and right, right? We're also talking about the tree travelers. So tree travelers is basically, I give you a root node. I need you to print out all the values, right? The values of all the nodes in your tree. Okay? So the way we're doing here is we check if your left tree is not empty. Then we what? We're calling the print tree function of the left tree. Remember, there are subtree, right, in the whole tree. And there are subtree of another subtree. Okay? So we can handle all the subtree at the same, right? So we print out the left tree if it's existing, and then I print out my self value, right? And then I print out my left subtree. Okay, so that is a recursive function, traverse we learned, right? Why are we using recursive function, right? Jeffrey, do you remember what is recursive function mean? Jeffrey?
What do you say?
The question is, what is recursive function mean?
Okay.
Do you know?
Yeah. I think it's a function that calls other functions.
Calls other functions.
So the function calls print.
Aston, do you remember what is recursive function mean?
No, I'm not sure.
Okay. Recursive function means a function call himself. Okay? A function call himself. Right? Why I say that? Because if you look at the print tree, it is a recursive function. Okay? I'm calling himself, right? But on a different object. Left subtree to the print tree. But you can imagine when I go to the left subtree, it will call his left subtree again. So it's recursively. Because I don't know there is a beginning or ending. Right? And because my whole object, right, is similar and consists with a similar subpart. Okay, so in this case, I can use a recursive function to looping all the parts. Okay, never mind. Okay, we're gonna learn use this recursive function more in the future. Okay, but just keep in mind, recursive means function call himself. Okay, and so today's class, right, I want mainly to starting from talking about the traverse again. Okay, so I go back to the assignment we did last week. Okay, this assignment, right? I run that. Go to print tree. Okay, it basically to the traverse and print the value of every node in the tree. Okay, so today I'm gonna first talking about the traverse in tree. Okay, based on the order of the traverse, there are 3 different traverse way. Okay, the first way called in order. Okay, and you can see the printout or the traverse order is left first. Okay, and then root basically the middle, right? The middle node, right? And then right. Okay, what does it mean? Look at this example. Root node is 1, right? It has left node 2, right node 3, and the left node 2 also have his left node 4 and right node 5. Okay, so suppose I'm trying to in order traverse the whole tree when I give you the 1 root node, right? It will do what? Traverse of the left subtree first, and then himself, and then the right subtree. That's called in order. The second traverse way is called pre-order. Right? Pre is like happened before, right? Happened before pre-order. So let's look at here. The pre-order is basically traverse the node in order of root, left, and right. Right? Still 3 parts. Left side, the right side, and himself, right? But the difference is I print out myself, or I visit myself firstly, and then left side, right side. Okay? The last traverse way is called post order. Post is behind, right? So it basically means I traverse left, right, and then at the last I traverse myself. Okay, so if you just look at the three different ways from the standard of the root, also the middle node, right? The way different is when you're gonna visit the root node. The in order means I visit the root node in the middle, left first, then root node, then right side. That's called in order. Pre-order or pre-order means pre-visit. Okay, pre-visit who? Pre-visit root node, right? The root happened first, and then left, and then right, right? Left, right. They never change order, right? Left is always happened before right. The post node, right, is what? First, visit left and the right, and at the end, we visit the root node. Okay, if we take the exact example by looking at the example tree here, right? 1, 2, 3, 4, 5. If we travel the tree in the order, the final print out will be 4, 2, 5, 1, 3. How do I understand that? Let's imagine, right? Starting from the root node. Okay, and I need to visit the left subtree first. Okay, left subtree is here, right? So in the left subtree, my root node is 2. My left node is 4. My right node is 5. Right? But recursive, right? The same way we handle the big problem gonna be applied to handle the small problem. So here we have a small tree. So for this tree, again, we need to visit left first. Left, root, and right. The left is what? 4, right? So that's the reason why 4 node value is printed out first. And then middle, the root is 2. Okay? And then the right side is 5. So what do you find? I found the whole left subtree already visited, right? Visits completely. So then if the whole left subtree is visited completely, I'm gonna visit the root one, which is 1 now. Right? After I finish the root 1, I go to the right side. The right side is simple because you only have 1 node 3. That's the reason why the final output of the in order traverse is 4, 2, 5, 1, 3. Are you guys following? Aston, any question?
No.
Clear, right?
Yeah.
Okay. Louis, you there? Hello, Louis? I cannot hear you clearly. Too low. Your voice too low. Okay, Julian.
Yeah.
You understand how we are travelers in order, right?
Yes.
Okay, so can you explain to me pre-order, right? In the same way how I explain in order.
Okay, so it goes from the top. So it goes from the root to the.
Okay, first print out who?
So it goes from root to left, and then just. I don't know how to explain it. It just goes in one way until it stops.
First, visit root one, right? So who is the root one? When I give you this tree, who is the root?
1.
1. Okay, so I print on 1, right? I print on 1 first, right? You see the 1 here?
Yes.
And then what? The left subtree, right?
And then it prints left 2 times.
Right? The left subtree is what? 2, 4, 5. If you look
Yeah.
at the left subtree, again, I need to do root, left, and right, right? So the order is what? Root is 2, 2, left is 4, 4, right is 5, right? After we complete the whole left side, we go to the right part. Right part is 3 only. Clear?
Huh?
Okay, Victor.
Okay.
Do you understand?
Yes,
Can you explain me the post order?
it starts from left, which is like 4, I think, and then it goes right, and then all the way back to root.
Okay, so first go to left, right? Who is left part of number 1?
Left would be 2.
2, 4, 5, right? This is the subtree, right? And then come to the subtree, we visit left first. So we visit to which one? 4, 5. Which one first?
4.
4.
I mean 4.
4 is left. We visit left
5.
first.
5 is right.
4, then right. Right is 5, right? And then back to whom? Back to the root.
Back to root, which is 1.
Root is here. The root is 2. The subtree, okay? Right? And after the whole left subtree is completed, we go to where? We go to the right part. But this right part is the node 1 right part, right? Which is 3 only. 3. And at the end, what? We print out the root. Clear?
Huh?
Okay. So now let's take a look at how we write the 3 different traverse function. Okay. So I'm gonna go to this one. So I'm gonna continue from the previous code. Okay. Same thing today for your assignment. You need to continue from your previous assignment code. Okay. So here, I'm gonna create a new function called in order. Okay. So in the in order function, I'm gonna in order traverse the whole tree. Okay. Similarly, okay, if you look at here, this print tree, if I'm asking you, what kind of traverse way this print tree function doing? Jeffrey? Jeffrey, you there?
Yeah. What's the question?
We're just talking about in order, pre-order, and post-order. Now
Okay.
I'm asking you, which order this print tree function doing?
Left,
What?
pre-order.
Why do
Actually,
you
no.
think
I think it's in order
why I think it's in order?
because it says def in order.
This is a new function created, right? Right now I'm asking you the print tree. Okay, I'm asking you the print tree. Aston, which type of order print tree is doing?
What's the question?
My question is, by looking at print tree function, what type of the traverse we are doing here? In order, pre-order, or post-order?
In order.
In order. Because we have print the root node, right? In the middle. Only 3 stuff, right? Left, right, root. In order means the root is in the middle. Pre-order means the root is happen first. Post-order means the root is visited the last. That's it. Okay, so we're gonna implement, we're gonna a little bit different, okay, for implement the in order. Because earlier what we're doing here is we print out the value line by line, right? No, it's not it, right? I wanted to have how we print out the linked list, right? Connect by the arrow. It will be easy to read. So in order to do that, we need to have a string to contain the concatenate the string, right? What we do is we're gonna have out string, okay? At the beginning it's empty. And then in order means what? Left, root, right, right? Check the left first. But before you are travel the left subtree, you always check if my left is existing or not. Okay? And then if it's existing, what we do is we can add the string from my left subtree. Okay? So I'm gonna say that in order it should be self.left.in order. Okay, what I'm doing here, I visit my left tree, and my left tree is supposed to return a string, right? Again, we can write in a function for this. What does it mean? It means the function is return a string. Okay, so here, my whole left subtree in order travel is return me a tree, return me a string, right? And here, of course, I need to add my self value. Okay, right side similarly. Okay, upstream self.right.in order. Okay, that's it. You can see the logic is very similar as print tree, but the only difference is we are returning the tree, returning the string, right? Instead of to the printout directly. Why do we need returning the string? Because we want print the string, the container string in one line instead of multiple lines, right? So now if I do in the print, right? Command this. It's not that's right, okay. I'm gonna do root start in order. Okay, so I do that. It give me error, right? It said only concatenate string, not integer. Okay, that is a familiar error because we're using add. Add string means concatenate with string, but remember, you cannot concatenate a string with a number. Why we have a number? Where the number coming from? Because my value of the node here is all number 3, 8, 10, 1, 6, 14, 4, 7, 13. Okay, what we're going to do, right? We're going to do the convert from a number to a string where we concatenate with the other string. I run that. Can only concatenate the string, not. Okay. So this is line number 20, right? Now number 20 here. Self.left in order. Okay. I know why, because I forgot to return the out string. Why? Because we are expecting the string is returning from the function. So if I not return that, what happens is this function call and return nothing. Okay, so run this. Nothing happened. Why nothing happened? Okay, look at here. I'm returning a string, but again, the string will not be showing in the console directly, right? You need a print string, right? Let's look at this. Okay, pretty good. But again, this contains every number, right? You cannot even tell it's a 1 digit or 2 digits. What we do, when you add the value, you add some separator, right? Okay, this looks good. 1, 3, 4, 6, 7, 8, 10, 13, 14 in one line. Perfect, right? And if you wanted to remove what the last one, unnecessary separate, right? You can do here. Look back to this, right? We learned it before, right? Because a string is nothing. A string is array of character, array of letter. So I can handle or I can cut the whole string by using the range index. Okay, -3. Jeffrey, what does -3 means here?
Next to 3.
-3. What does it mean?
What's negative 3?
Did you look at my screen?
Yeah, I am.
-3. What does it mean?
Oh, -3. It's the index.
What's the impact?
What's the impact?
Yeah.
I think it changes the order.
Oh, it's not changing the order. I give you an array, right? You are using negative index. Using the index range. What are you doing? Julian, what is doing here? We used last time, right? I remember in the linked list, right? This means, again, a string is an array of the character. I'm using -3 index range. It's basically what? Delete the last 3 characters. Okay, why? Because I have the last arrow, which is unnecessary, right? So if I run out here, you see the last 3 characters get deleted. Okay, so that's some tips. Okay, great. So then we did the in order, right? Let me print out some comments here. Right? Print that printing tree in order. Very good. Right. Now, similarly, we're gonna implement pre-order and a post-order. And let me tell you, that's very simple. Why? Because we know the only difference between the in order, pre-order, and post-order is the order, right, of visiting the left part, the middle part, and the right part, right? Now, if we said that pre-order, okay, same, functional return string. Okay, we are also using our out string to contain the value. And then I return out string. Okay. Now, which we need to write first? Aston, which part I need to write first? Aston? Hello, Aston, you there? Pre-order means I'm gonna visit the root node first, right? Let me using single quote, right, to be consistent. And then what? Basically, you can basically copy, okay, copy paste. Because as I said, right, the logic is the same. It's only different, the order different, right? So now let's see. If I said print out in order or in pre-order, will be different. Pre-order. Oh, by the way, I should show the tree. Otherwise, how are you going to tell it's correct or not, right? Sorry about that. So now let's look at the tree. The tree is, I think that's a tree. All right, let me copy it now. Okay, that's a tree. Okay, so now let me go back to the code. Let me remove it up a little bit. Now look at the compare here. Okay, so where's my tree? This is my tree. Okay, first, print tree in order. Okay, in order means what? Left first, middle, right. Okay, now let's work. It's print on one first. Why print on one first? Starting from the root, right? Always. First, to the left part. Okay, left part, this tree, right? And do I have a pencil here? Pencil drawing. Okay. This is my what? Left subtree. Okay. And then when we come to the left subtree, again, it's still in order, right? So which means I've read it to the left part first. This is my left part. So one gonna print out first. Okay. Left down, my middle. But when you're talking middle here is the subtree first, right? Because for the 8, the whole left is not down. But for the subtree, my left part 1 is down. So now we print out the middle, root 1, right? 3 is print out. Okay, left down, middle down, right side. The right part is also a subtree. Again, left first. 4, 6, 7. 4, 6, 7. Okay, so as for 8, is my whole left subtree completed with it, right? Okay, so now I'm gonna print it myself. After that, right part. Right part, I look at here. For the 10, ideally, we need to print out what? Left. Do I have left? I don't have left. So then I print out 10 first. And then the right part is 14. But can I print out 14 directly? No. As a subtree, I'm always looking my left first. Do I have a left? Yes, 13. And then print out 13. And then print out 14. Right? If 14 has his own right, like 15, 15 will be here. Are you guys following? Right? Aston? Clear?
Yeah.
Okay, so now let's take a look at the pre-order. Pre-order is root for the middle, left, right. Okay, 8. Of course, I print out 8 first, my middle. And then left. Oh, left is this. Right? I think something wrong here, right? Again, when we do the recursive function call, pre-order, right? You make sure call it consistent function because I'm doing pre-order. So when I do the subtree, is this pre-order also, right? That is a good demo to you guys. Okay, don't make the same mistake when you do your assignment. In order travels, make sure your subtree is also doing in order, right? Pre-order, make sure his subtree is also to the pre-order. Okay, let me run again because I was just realized the printout is not correct, right? And I just find out that's a problem of the way I'm calling the wrong function. But back here. Back here. Hold on 1 second. Okay, sorry, back here, right? So when we say print order, okay, root first, 8, and then go to my subtree, sub-left tree. The sub-left tree, again, the root first, 3, right? Down root, the left side only 1 node, then print out 1. Right side is also a subtree, right? Again, the root first, 6, and then left, right. Okay, the whole left subtree of my 8 is complete, right? And 8 is also complete at first. Then I take a look at the right side. The right side, again, root 10. Do I have left? No, I don't have left. I go to my right. Okay, for the right, I go to my root, which is 14 first, and then 13. Right? So it is 14, 13. Very good. Now let's quickly take a look at the last travel, right? Which is pre-order. So what I'm gonna do here is I'm gonna say post order, which is left to right node, right, left to right middle. Okay, I just need to make sure I'm calling the same recursive function. Okay, so now I call that. Printout tree, right? Let me add in the post order, in pre-order. Okay, post order. Run this. Okay, now let's look at the tree again. Okay, so post order, left, right, root. Root is the last. Okay, now let's look at 8. Left first, right? Left first. And then, sorry, hold on 1 second. Okay, so look at the left part, right? And then I'm gonna look at the left part again. Wait a second, hold on. The pre-order and post-order the same, right? Something is wrong. Okay, something is wrong. So let me quickly check the code. Didn't I call the correct function? Post-order. Oh, yeah, very stupid mistake, right? Because I just changed the function name, but I didn't change the order. Remember, right? So here, just make sure you are in candidate, right? You are visit the root node up, left, and right. Okay, that's correct. So you see, the three functions, they are very close. They are very similar. The only difference is where the place you visit the middle one. Okay, I run this. Pre-order. Okay, I run this. Now this is correct. Quickly go back here. Okay, so I print on tree in the post order. Left first. This is the left part of 8. But again, this is the left part of node 3. Right? Do 1 first. Right? 1 first. And then, do I need to print out 3? No, because the root one is with its last. Go to the right side. The right side, left, right, root. 4, 7, 6. I done left, I done right, right? I go to my root. 3 print out. Okay, so I complete the whole left part of 8. Okay, now we need to move to right? Because left, right, middle, right? For the right part, I don't have left, but I do have right. Right, for this right subtree, I go to my left first. 13, 14, I done my left, I'm done my right to my root. I done the whole right side to my root. So in the post order, you can see the most root node gonna be print out at last. That's it. Okay, so come back to our slides. That's a 3 different order. And then let's go back to the BST again. So last week we already talking about BST. BST is stand for binary search tree. We know binary, right? Binary means at most 2 child nodes. And a search tree, based on the name, we know, hey, this tree is something related to a search algorithm. Let me tell you, that is one of the fastest search algorithm or data structure you can learn, okay, in the programming. Why? Because it's not just a binary tree, okay? It has very specific character, okay? Aston, do you still remember what is the specific difference for the BST tree?
The left value has to be less than the parent value, and the parent value has to be less than the right value.
Yes, correct. The left, actually, you know what? To be more accurate, I don't think I need including the equal part. Okay, I don't think I need including the equal part. That will be easy, right? So left always smaller than parent, and parent always smaller than right. which means what? If I'm the parent, if I'm the root, I'm in the middle. Okay, that's the same thing. I'm the middle one. Okay, if you are smaller than me, go to my left. If you are bigger than me, go to my right. What does it mean? I give a tree. Okay, look at this example. The root is 56, right? His left node is 30, less than 56. His right node is 70, bigger than 56. And you're going to find in all the subtree of the whole entire BST tree, the rule is applied to every subtree. 30, 22, 40, right? 22 has only one left node, but which is smaller than him. 2, valid, right? And if we have a 11 in the middle, 3, 15, good. And what you found? You found all the nodes on the left side, right? Not just his child node, okay? All the nodes, his child node and his grandchild node or the descendant child node are all fewer or smaller than the root one. Is it right? 56. You found all the nodes on his left is less than 56. Okay, that's very important. On the other hand, the right part is always bigger than the middle one. Okay, the right part is always bigger than the middle one. And look at 3 statements here. The left subtree of a node contains only nodes with keys less than the node's value. The right subtree of a node contains only nodes with a key greater than the node's key. The left and right subtree each must also be a BST. What does it mean? The BST, every subtree, right? Every subtree has to follow the same rule. Okay? Has to follow the same rule. Otherwise, it's not a BST tree. Okay? Jeffrey, are you listening?
I am.
Tell me, what's a criterion or what's a judgment I made to decide if a tree is a binary search tree?
It follows a specific inequality line.
Inequality line.
Okay, so the subtree only contains nodes lesser than the key.
What about right side?
It's greater than the key.
Sorry, hold on 1 second. The incoming call, 1 second.
Okay.
Yeah, sorry about that. Okay, so you're right. Okay, we check the left is smaller than middle, right? The right is bigger than middle. And again, all the left nodes, not just his own child node. Okay, now let's take a look at the example. It is a binary tree. Jeffrey, tell me this is a binary tree or not?
It is. I think it is.
It is
Yeah,
a
it is.
BST, okay? BST.
Yeah, it is a BST. Because
Middle one is 8, right? Yeah, go ahead.
Yeah, because the left ones are less than 8 and the right ones are greater than 8.
Not just 8, again, not just 8. You have to take a look at all the subtree. Okay? Louis, you there?
Yes.
Is this a BST tree?
No.
Why?
Let's have
Why? Huh? Why?
because it doesn't have like more than 3 nodes on one node.
I cannot hear clearly because what?
I don't know.
Okay, which means you're not listening to me. Okay? Victor. Victor? You did the binary search tree?
It's a binary tree because the childs are like are 2 and less than 2.
Which one are you talking about? Which node are you talking about?
The second one?
Yeah, I'm talking about this one, second tree, right? If the second tree, the binary search tree.
It's a binary tree.
Why?
It's all less than 2.
It's all less than 2. Which is less than 2? Tell me which node is less than 2? Right? Julian,
Huh?
is it a binary search tree?
The what?
Is the second tree is a binary search tree?
Yes, it's a binary tree.
Aston,
I don't think it's a binary tree because for the root node, the left value is greater than the root when it's supposed to be less.
yeah, it's so obvious. How come you guys confused? Well, what I said, left smaller than middle, right is bigger than middle. That is meet the requirement, right? 7 is bigger than 2. How come the 7 appear in the left side? So it's definitely not a BST tree, okay? What about this? Jeffrey,
This is the third one. I think it's wrong.
why?
It's not a BST
Why?
because it only has one right. It only has one subset.
But does BST tree said I have to have 2 child nodes? It is a BST tree, okay? And it is a binary tree, right? Because binary tree said at most 2 child nodes, right? It then says you have to have 2 exactly child nodes. So 1 node is allowed. So this tree is a binary tree. It is also a binary search tree. Why? Because the right side is always bigger than middle. Victor, what about this? Victor?
Yes.
Okay, that's correct. It's a BST tree. Why? If you look at every node, make sure you look at every node, okay? 50, all the left side is smaller than 50, right? 17, 9, 23, 49. The right side, right? All the nodes right side is bigger than 50. Okay, and if you take a look at the 17 subtree, same thing. All the left nodes is smaller than 17, or the right nodes is bigger than 50. Okay, Aston. Yeah, the last tree, binary search tree.
One.
The last one, this one, the right blue one.
Yeah, it is.
Are you sure?
Yes.
Have you look at every node? Anybody find out? I can tell you it's not a binary search tree, right? Anybody find out why? Anna?
It's because for 15, the 18 isn't really it's the left node because there's no right. It's the left node because of the first. It's like the first child.
No. 10, 15 is right? Right is bigger than middle, which is right. 18 is bigger than 15, that's right. So this part is right, not here. Not the problem, it's not the problem. Anybody found the problem? The problem is 12, okay? If you look at the 7, 12 bigger than 7, right? 2 is smaller than 7. So it looks like it's a valid BST subtree, okay? But if you look at 10, the 12 is appear on the left part of 10. Am I right? What did I say? All the left nodes has to be smaller than the middle one, but 12 is not smaller than 10. So it's not a valid BST tree. Okay, so that's very important. You have to remember all the nodes on the left smaller than middle, or the right nodes are bigger than middle. Okay. Okay. So we have understand the BST tree. Now let's try to construct a BST tree. To construct the BST tree, I mean, this time we will not manually to create the tree and connect left, right, left, right, right. Because we have the loop, right? We have the loop. So we're gonna write a function to do it. Okay, so look at this example. Basically, when you do the insertion in a BST tree, you need to follow in the rule and find the right place to insert the node. Why I say that? Okay, suppose you have a root 8. Okay, now I said insert the number 3. You can only insert on the left side, right? Because 3 value is smaller than the 8. I give you 10. The 10 can be only insert on the right part. Okay? So that is the whole logic we're going to implement in the insert function. Okay? Guys, listen carefully. Okay, I gotta ask you to write it. Basically, the whole function is merely solving the problem to find the correct place to insert. Okay? Insert left if the value is less, insert to right if the value is more. If you look at this function here, what I'm doing, I do insert, okay? And I'm crossing the root node and the key, The key is just the value, right? The value of the node. Okay, you can call that value, you can call that data, you can call that key. It doesn't matter. Okay. So what I'm doing first is I first check if root is none. Okay, and that root doesn't have to be the most top root, right? It can be any places in the tree. So if the root is none, I'm gonna return an object of the node, right? I create object for the value key, return back. Okay, and if the root is not none, so which means if the root is not none, which means what? Which means we are checking some existing node in the tree, right? Then I'm going to check the value. Why am I going to check the value? Because the BST tree had the value loop. Left smaller than middle, smaller than right. Right? So I'm checking if the root value equals to the given key. What does it mean? Which means there is existing value in the tree. Okay, there is existing value in the tree. So I return the root, right? I return the root directly. If, else if the root, whatever the node I'm checking, his value is smaller than the new value, then, right, then the new value should be inserted on the right side of the checking node. Am I right? The new value is bigger than the checking node value. Okay, it's bigger than me, go to my right. Okay, so I said root.right equals to insert. Okay, here, very important. We're using recursive function again. Did you notice here? We call the insert function again, but we are calling insert function against the subtree. Okay, root.right. So I'm parsing the whole right subtree at the, parameter, right? And then parsing new value again. So which means what? I know you are bigger than me, then you should insert some place in my right side, right? But which part of the right side they're going to insert, I'm not sure. You go to my right subtree to ask them. Okay? That's the logic. Similarly, right? If it's not equals to, if it's not smaller than, if it's not equals to, if it's bigger than, or it's otherwise is smaller than. Only three cases, right? We compare the value. So if the new value is smaller than the middle one, which means what? Oh, I know you should go to my left tree, but I don't know which exactly position you're going to insert it. Don't worry, okay? You go to ask my left tree, right? I call the insert and pass in my left subtree and new value. And the return and assign to my left. Assign to my left. Right? And at the end, I return the root. Because why? I already have the left, I put the right, I return it. Okay? So then you may ask me, still confused, right? How it is inserted. Let me write the code and let's test it one by one, okay? So first of all, let's write the code. Okay, I have the tree. So I'm gonna have the insert. And be careful here, pay attention here is I didn't include the insert function into my node class. Okay, till now, some of you guys still confusing about indentation, right? Indentation decide the scope of the function, right? if we have indentation inside the class, which means all the functions belong to this class. But here, I will not include that. It will not be part of the node class. It's just a standalone function. The function gonna take a node. I'm gonna put in node. I think it will be easy to understand, right? I'm gonna put in a value or put a new value. It will be easy to understand, okay? So in this function, again, I need to check, right? I need to check if the node is empty or not, right? And in the early code, it said is none, right? Of course, you can write it like that. You can write it like that. But there's another way to do that is if it's none, so I said if not node. That's the same condition. You understand this negative logic here, right? If node is none, which means what? Which means when node is none, this if condition 2. Okay? So if I write it like that, what does it mean? When the node is none, then not none is true. Okay? So the condition logic is the same, just like different writing, right? If it's not none, what am I gonna do? If it is none, right? If it is none, I return the node with a new value directly. That's the first case. Second case, else. Else means what? Else means, hey, the node is not none. Okay, if it's not none, now it's time to compare the value, right? So we said if the node value is equal to the new value. Okay, they are equals, which means existing. So I just return the node directly, right? It give me the arrow. Why is give me the arrow? Juliet, why does give me the arrow? Invalid syntax. What's the problem here? What I'm doing here, I'm doing the comparison, right?
Because there's no value for new val.
There's a new val.
Oh wait.
I mentioned to you, right? I'm doing the comparison. Am I doing the comparison correctly here? Aston, did you find the syntax error here?
No.
Comparison. Okay. Comparison is a double equals. Okay. Okay. So else if the node value what are they? If the new value is bigger than the middle one, bigger than the checking node, right? So it should go to left or right. Jeffrey, the new value is bigger than the current checking node value. It should go to the right side or left side.
The right, left.
Huh? Go to the right or left? Jeffrey. Jeffrey?
Do you hear me?
Yeah. I'm asking you.
So I think it's the right side.
The right side, correct. Right? The new value is bigger than me. You should go to the left, you should go to the right side of me, right? So what I do is then know that the right side, right, equals to insert. I don't know like which exactly part you're gonna be, but you know what? I'm just pausing you, just like a pausing ball to my right subtree. Okay, my right subtree. Okay, and else not equals to, not a bigger than, and smaller than. If it's smaller than, I go to my left, right? Insert
Love you too 吗？
node dot left, new value.
还在上课呢？那啥呀？
你要认真听。
那是啥呀？
作业
那啥呀？给我的吗？
Okay, so then, okay, so let's continue. Yeah, I complete the function, right? Let me repeat again, right? Insert, first I'm checking if the node, this node partial node, right? It can be subtree. It can be subtree. If the subtree is none, I return a new node, right? Otherwise, I compare the value. Value is bigger than the checking node value, go to the right side. Very important, go to the right side. And then if it's smaller than my values, go to the left side. So now let's take a look at that, right? I'm gonna delete all of it, okay? And I'm gonna keep only left, right. I go to the pre-order, okay? I go to the in order. I go to in order, right? Because in order, the left, middle, right is basically going to be from small, medium. I mean, from the value perspective, right? Small, medium, right? Bigger. Okay, so now if I only have one node first, okay? I run this. Something wrong with the wrap up. I think it's not running. Okay, it's running. Pretty straight in order. Okay, it's 8. Okay, I have one node now. Now what I could do? Insert new value, right? If I look at the example we have here, I insert a new value 3. Okay. I insert a new value 3 to the current tree. Run this. Okay. 3, 8. 3, 8 means what? 3 is left, 8 is middle, right? That's the reason why left, middle, right. When I print out. So which means the 3 node is inserted to my left part of the tree. Okay. So if you look at the function, what it's actually doing, right? If I set a breakpoint, not can. So let me explain it. Okay, node 8. I call the function, the root node is 8, right? Come here. Okay, this node is node 8, right? Is my node 8 num? No, it's not num, right? Okay, I'm checking the value. Hey, is node 8 equals to 3? No. Okay, now is node 8 is smaller than 3? No. Is that come here, right? Node 8 is bigger than 3, or the new value is smaller than the 8, right? I go to my what? Left part. So node 8, left part is num, right? When the left part goes to the function, it's checking, hey, is my left part is num or not? Yes, it's num. What do I do? Oh, I create a new node and return that. So this new node is 3. When I return this new node, where the returning going to? Remember, the returning come here. And this new node created a set at the left child node of the previous node. Aston, are you following? Aston, you understand what I'm talking about here?
Yeah.
It's checking 8 first. And it's come to this condition because why? 3 is smaller than 8. in this case, I know 3 must go to my left side. Okay, so I'm calling this function and passing my left. 8, the left subtree of 8 is none right now. It's empty. My left side is empty. So when I call this, okay, come here, it's checking, hey, the left node, the node is none. So what I'm doing, I'm just creating new node object for the new value, which is 3, and return that. I return an object node. And this returning from here, it will be set to my left side. Whose left side? 8 left side. That's the reason why the tree is constructed as 8 in the middle, 3 in the left. Insert root 10. Run this. 3, 8, 10. We know 3 left, 8 in the middle, 10 right. How it happened? Okay, when I insert the 10, I already have 8 and 3 in the tree, right? You know what? Let me have in this. Okay, look at here. Okay, don't worry about the 1, 6, 7, 4, 7, 13. Okay, so I have 8. Okay, I have 8 and 3. Now I'm go to 8 first, right? Notice 8. 8 is not none. This is 10, right? It's 10. Okay, so it's come here, right? The new value is bigger than current value is 8. Okay. Oh, you should go to my right side. And when said 8 are right, at that time, which is none. Okay, so we're going to call the function again, passing num and 10. So come here, notice none now, right? Notice not 8 now, right? It's called the function again, it's num. There's no num, then return 10. Return the node 10. Return to whom? Return to the previous call, 8 dot right equals to node 10. That's the reason why you insert the node here. Okay, so that's why when print out the tree, it have 3, 8, 10. Now, once more, right? If I insert root 1, okay, so now what I'm having here, I'm already having this tree, A3, 10. Okay, A3, 10. Let me write it first, right? 1, 3, 8, 10. This insertion is correct. Why? Because it's starting from left, middle, right, left. This is in order travels, right? 1, 3, 8, 10, which means write it insert at the correct position, right? As a left of the node 3, right? So let's look at here again. Root is 8. Okay, it's 8. New value is 1. I'm checking, the new value is smaller than 1. Smaller than 1 node. That's fine. Let's go to my left node. My left node is who? Is 3, right? Yeah, 3. So now this time, node it becomes 3. Same thing. Let's come here. Hey, 1. The new value is even again smaller than my subtree root 3. I go to my 3 dot left. 3 dot left here right now is none. Right now is none. So then when it's called again, this is none. It return node 1. And this node 1 gonna set to the 3 dot left equals to node 1. That's it. So he added the node 1 the left side of the node 3. Julian, are you following?
Yes.
Do you understand it?
Yeah.
Okay, so basically by using the function, you don't need to worry about this node is gonna be inserted where. Okay, you add a 6, you add a 6, you add a 4, you add a 7, you add a 13, 14. When you call this function, right? When you call this function, it will always helping you to insert the value in the correct place, right? Okay, that's it. That's an insertion function in the BST. Okay, I know we are running out of time, right? But I still want to finish this one. We have the way to construct the BST tree. Now is the time to use that. Again, what I said, the most biggest advantage of using BST tree because it's faster search number. I mentioned in the array, in the linked list, the way we can find out a number is you have to go through from the beginning to the end until you find the number, find an item, right? That's it, because you don't have other way. But for the binary tree, because it has a character, left side is always smaller than the middle one, the right side is always bigger than the middle one. I have a better way to do the quick search. Why? Because think about that, right? If I have this tree, okay, let's take a look at the tree again. I'm asking you, does number 6 existing in the tree? How you do that? Right? Either. I'm checking from the root. Okay, I'm checking from the root. Hey, is the target number 6 smaller or bigger than 8? If it's smaller, we know we only need a search on the left part. The right part is bigger than 8. I don't need to care because my target looking for number is 6. So I basically dump half of the tree. Again, come to 3. Is my number 6 is bigger than 3? Yes. So I go to the right part. So same, I dump half of the tree. So every time you do the search, you dump half tree, dump half number, dump half data. Your search is faster because you don't have to check every number. You reduce or you narrow down the search scope. Clear? Ashton, I understand this?
Yeah.
Okay, so now let's quickly to implement the search function. Okay, so that is a search function. Okay, I already give to you. It's just like what I just explaining. You try to search if a value exists in the loop, exists in the tree. What are you doing? I'm checking if the node, or I'm checking num, or what, or the root value equals tree. Hey, I found the root. I found the node. I return the node, right? If the key or the data or lookup value is bigger than the node value, I know I go to my right side, right? I go to my right side. But if the value is smaller than the node value, I go to my left side. That's it. Very simple. search, node, and the target. Okay, I'm changing the variable name, make it more, straightforward for you to understand. Okay, again, we are try to looking for a number if that exists in the tree. You check if the node is none, or the node value is equal to target value you're looking for. Again, double equals to, okay, don't forget it. You found it. Return the node. Right? If the node value smaller than target, oh, the target number is bigger than you. So go to my right side, right? Go to my right side. Return the search my right side subtree, because you're bigger than me, so you can only existing in my right subtree. You recursively passing the same function against your right node. Okay, and then if this condition is not true, the only left case or scenario is what? Is the target is smaller than me, go to my left. Right, go to my left. And you may ask me, hey, why you are not writing like a if else, something like that, right? You can do like that, but let me tell you, that's the same effect. Okay, you can omit one else, because why? If condition is not meet, right? You're running here, this is the same thing as else, because that's the only different cases. That's it. So let's try that, right? 8, 3. Okay, now let me try to build up the tree. Okay, so insert 6, insert 4, and insert 7, and insert 10. Oh, we already have 10. Insert 14, insert 13. Now let me print out the tree. That's my tree. Okay, this tree is this tree. Okay, this tree, right? I do the in order print 1, 3, 4, 6, 7, 8, 10, 13, 14. Yeah, that's an in order print out of the tree. So now I want to set, okay, try to print it said look up node in tree. Okay, we said that we call the search function, right? Search function, the root node, okay, the value, right? What are we having here? Okay, let me see if I'm looking for 6. What happened? Okay, look up node in tree. It's returning the node. That's correct, right? Which means it's find the number, right? It's find the number in the tree, right? What happens if I put 16, which is not existing in the tree? Print out, it give you none. Right? Try the other number like 13, right here. Run that, it print out the node. Why? Because I'm returning the finding node. How I do the searching? Either I check the value. I come here. First, I'm checking starting from 8, right? The root is 8, right? Root is 8. Hey, 8 is 8. Root is 8. Okay, I'm looking for 13. Okay, 13 is bigger than 8. Okay, I go to the right part. Right part I'm checking with, I'm compare against 10. 13 is bigger than 10. Oh, I go to my right part. Right part, I have 14. Okay, is 13 bigger than 14? No, it's more than 14. Then it's go to my left part. I left part and checking the node. Oh, it's 13. Oh, it's equals to the value I'm looking for. Right? So I'm returning this node. So this node can return. Right? What happened to 16? If it's 16, I compare it's 14. Bigger than 14, go to my right side. But do I have a node in the right side? No. The right node is none. So it's returning none. Right? It's returning none. That's it. Okay, so today we learned 3 different ways to do the traverse. We learned the function, how to insert a new node into the binary search tree. And also we learned the search function, how we look up if a value is existing in the tree, in the BST tree, by using the feature of BST tree. Any more questions? Julian,
Huh?
do you have any more questions?
No.
It's clear for you, right?
Yeah.
Victor,
I understand.
you understand it, right? You understand it. Very good. Okay, then that's it. Okay. So again, right, in the assignment, I'm going to ask you to implement the 3 different traverse way and insert function and search function, right? If you listen carefully during the class, or even you go back to check my video, it's not difficult to write it again. Okay. But of course, if you have any question, if you still don't understand how this is working, right, you can attend Saturday night Q&A, right, or just send me messages. Thank you so much, guys. That's it. Have a good night. Bye-bye.